My name is Tim Watkins. I'm in charge of technical support here at Bonitron, and basically today I'm just going to talk to you about common busing and sort of issues that occur and other items that you should be aware of. So let's get going. All right, so I'm assuming that everybody has a basic familiarity with Bonitron products. We cover overvoltage solutions, undervoltage solutions, and power supplies for drives. Um, there are a variety of ways these can be arranged and configured, and today we'll be just talking about the common busing and the basics with that. Um, yeah, these are the topics we're just going to go over today. Basically, just how to actually connect it to your VFD, your drive, um, what certain advantages are of using the common bus system, basically our recommended solutions for that. These include the common bus diodes, um, the common bus DC power supplies, and the new product that we presented in last year, 2015, the Regenerative DC bus power supply. And also as a little adder, we'll talk a little bit about some problems with overvoltage design and some considerations you need to make when considering braking solutions on a common bus system. So let's just start with the drive and looking at this. So a common bus is effectively just connecting the DC bus terminals of two or more drives together and configuring them into a large distributed bus. You can think of this as basically making a very large filter capacitor because you're just placing in series, or correction, in parallel, all of these capacitors on the DC bus. These are marked on the drive either typically as DC plus or DC minus. Just depends upon the drive manufacturer how they label these. The important thing is that you do not connect to the braking terminals. These are for the braking resistor, and if you connect to these, basically the DC bus will not operate properly. There won't be, appropriate energy sharing between the drives, nor will any braking solution attached really function if you're connected to the braking terminals. One thing to note is this is the DC link choke. Bonitron needs to connect to basically the drive capacitors as close as you can get to these connections. Often there's a resistive precharge or precharge contact in the way, but as close to these connections as you can in the drive topology. The DC link choke, if you connect to the rectifier side of this, if you were to connect here, basically with our braking solutions, this creates basically a boost circuit, and damage will result to basically the Bonitron equipment and Bonitron products. So it's very critical for any of our products that we connect directly across the capacitor if possible on the drive. So moving forward. So some things to consider when creating a DC bus with your drives. Inductance can result on the DC bus wires. This is just a result of capacitance and just the impedance that builds up. The reason we want to eliminate this sort of inductance is because this can result in voltage ringing over long distances. And the voltage rings are just very high little voltage spikes that occur when stuff switches on and off. So basically the way to minimize this is to place the largest drive you have as close as you can to the rectifier section. The rectifier section can either be the front end of the drive or the DC bus power supply. This is important because the larger drive will of course be carrying more current and will build up the most inductance. So you really want to minimize that DC bus length. You also want to minimize all DC bus wiring as much as you can. It's really recommended to place all your drives and all your common busing all inside the same cabinet if possible. Basically, there are a lot of recommendations from different drive manufacturers, but some recommend just using either bus bars, or if you're going to use DC bus cables, to add a twist, like one twist per foot. I would recommend you check with your drive manufacturer to verify this and just see what their recommendations are for common busing. So now, why would you want to create a common bus? Why not just have the drives operate independently and standalone? A common bus is just basically an energy sharing between drives. Um, one drive can be actively regenerating, basically absorbing energy from the motor and placing it back on the DC bus, while other drives in the system can be absorbing this regenerated energy. And by this, there's energy savings. You do not have to provide an external braking solution or resistor, braking resistor. So just basically how you design it can really save energy just on that alone, just even connecting the drive capacitors. If you do need an external solution, if you do have a lot of regenerative energy on your drives, you can just optimize with a single dynamic braking or regenerative solution, basically a line regen, and that way, all your drives can just operate off of one dynamic brake. I mean, dynamic brakes might only be used in a process, a few times a day, and if you can just have every drive use the same braking transistor or resistor, that can equate to amazing, just basically capital savings. You don't have to buy as much hardware. Common busing is also incredibly flexible. Like there's so many different design options that there's no way I'll be able to get into all of them or address all of them at all. Basically, can be designed to incorporate drives as small as 1 horsepower all the way up to 1,000 horsepower, and you can do that all on the same bus if you are careful in your design. And of course, there's potential money savings just in terms of not having to buy as much hardware, being able to use a single braking solution, and being able to recapture and reuse that regenerative energy. So the solutions that Bonitron provides for creating a common bus. We provide diode modules. These are just basically modules that you use to connect your drives together. Just effectively attaching one drive capacitor to another, you need to use a diode module. We'll go into a little bit more in the next few slides as to why diodes are required, but Bonitron provides them. The product line for this is called an M3345CBM, and these are basically diodes connected to a heatsink on a plate with fuses. DC power supplies. These are power supplies that take the three-phase or single-phase power and output DC power to the drives. The drives will be powered directly from the DC bus. With the DC power supply, no diodes are required. Basically, it's just a very simple solution by providing a single power source for every drive. This connects the drives bus capacitors together, allows sharing, and it's, in my opinion, definitely the simplest design to go with, is just having a single power supply. The regenerative power supply, this basically incorporates a line regen that's been modified in order to act as a power supply. So this is basically a power supply and a line regen all in a single box. So this, basically is your braking solution and your power supply. So when the DC bus rises, this regenerative power supply can take the energy and place it back onto the AC line. So going back to the common bus diode modules for actually connecting the drives together, why use the diodes rather than just a simple distribution block? Diodes allow current to flow in a single direction. Basically, we just use this and design the diode module just basically to guide current where we want to go. The other way we guide current is basically each diode has a voltage drop of 0.7 volts. This drop is very small, but as you all know from basic electronics, that electricity flows in the path of least resistance. Basically, by utilizing these diode drops, we can basically get the current to go where we intend. Basically, you can share it amongst the drives, or you can guide it towards your external braking solution. So this is a picture of our M3345CBM. Basically, the drive connections are down here. There's fuses. The positive, DC bus connections go through here to this diode block. And basically, just very simple. And then there's negative side and comes out the other side. So the drives are powered by AC power, and basically the diodes allow energy to be shared amongst each drive. So if one drive is regenerating and the other drive is motoring, energy can flow from this drive straight into this one. If the DC bus gets too high and all the drives are in danger of overvoltaging, you can use an external braking solution, either a Bonitron line regen or a Bonitron transistor and resistor combination, and use that to basically protect your drives from having overvoltage faults. Our website has the list of the M3345CBMs we offer. There are a variety of current ranges going from basically from 10 amps all the way up to 300 amps. Our largest CBMs can handle up to 6 different drives and create a common bus for those. If you want to create a common bus for more than 6 VFDs, basically you need 2 of these diode blocks and basically arrange them and connect basically the regen terminals together. And that way you'll create an effective common bus using multiple M3345s. So when people think of diodes, they of course think of the single current flow option. And this leads to a lot of confusion with me having to answer trouble support calls, because people wonder why they see current flow both directions when they expected to see basically single direction current flow. Single direction current flow, these are traditionally known as steering diodes in the common bus world. Steering diodes are not currently recommended by Bonitron for designs. We do have this option, and we previously sold them, but we really don't recommend these for new designs. However, if you press us, of course, we will be happy to offer what we've designed in the past for you. Steering diodes are single direction diode modules. Their purpose is basically to isolate drives from each other, prevent that sort of energy sharing that you actually would like to have in common busing, and basically it only provides a source for the elevated power to go out to your external braking transistor or your external line regen. This is not a bad thing in and of itself, but there are a few issues which can occur with external braking modules, either the braking transistors or the line regens. And I'll go in a little bit more detail in the next slide about that. But we like the dual current flow because it allows one drive, which is regenerating, to be able to share its energy with a drive that's motoring. So that way energy is just consumed within the entire drive line immediately as produced. So, and you basically are creating a larger capacitor bank for all your drives. So this reduces, drive ripple switching losses and provides you with some ride-through capability. So basically going into a little bit more detail as to why Bonitron only provides basically sharing diodes, which is basically, our diodes which have been jumpered to basically allow current flow to flow both ways versus the steering diodes, is because basically the steering diode limits what you can have on a common bus and what your advantages can be. We do not recommend them steering diodes with use on a external braking transistor. Basically, if there's not adequate capacitance present and the diode only allows current flow one way, we have seen many cases where the braking transistor is damaged because basically it will result in damage to the external braking transistor. And the primary reason we don't go for steering diodes is that Bonitron does not really see a good use for them. Basically, you cannot share energy, and there has been like one instance in the past where basically somebody who had 4 separate drives, but they weren't grounded at the same place, and they had steering diodes. These steering diodes basically prevented the drives from basically seeing each other, and basically they had separate AC power inputs, and the grounds were floating with respect to each other. So our line regen was connected to all 4 of these drives, but there was a big voltage difference between each of these drive buses. So what our line regen saw was basically a huge overvoltage, was a huge voltage difference, more than 1,000 volts DC. And this kept on causing overvoltage faults on our line regen. And this was basically just traced back to basically common mode noise. And the way we solved this was actually by just sending a single bus bar to basically modify our steering diodes from basically just being steering diodes to sharing diodes, and allowing current to flow not only just one direction but the other. That way the drive's DC buses weren't floating with respect to each other anymore. our line regen was protected from overvoltage faults. Um, yeah, so that basically just saved the whole system, the whole design, by just allowing this current to flow in both directions. So our M3345CBMs, this is just going over the topology. Basically, there are two diode components. Each diode component contains 6 individual diodes. So basically, what makes it a sharing diode is that we provide this jumper, which is a bus bar, in between the one-sided diode and the other. And this allows current to flow back and forth and share. So going to a little bit more detail, if you were to imagine that if drive 1 was regenerating energy and drive 3 was motoring, the way that current would flow between drive 1 to drive 3 is that current would flow via this path from the positive. Well, electrons really don't flow that way, but just for the sake of imagination, electricity flows from positive, goes through this diode here, comes around, comes back to drive 3 out to here. Drive 3 absorbs this energy, and the return path is, of course, going through drive 3 negative, back through this diode, through this path, and back to drive 1. Over this path, over this current path, the electrons have passed through 4 separate diodes. Each diode, if you remember, has a 0.7 voltage drop, totaling 4.8 volts drop. So the important thing about this to realize is that circulation currents will not occur between separate drives unless there's like a really elevated voltage level, more than 4.8 volts. And that's because there has to be a potential difference for current to flow. So if there's a more than 4.8 volts between drive 1 and drive 3, then current will flow. The thing to remember is that if it's actually going to an external braking solution, if drive 1 was and the DC bus was so high that the regen was about to kick on, drive 1's current flow would be going to the regen positive, then from the regen negative back to drive 1. So then there's only 2 diode drops, 2 voltage drops going through here. And basically there will be a 2.4, or correction, this should read 1.4 volts voltage drop. So that's a typo. Apologize for that. Okay, so moving on to a common bus power supply. These are basically power supplies that take 3-phase power and basically rectify that into a DC bus. Bonitron provides 2 different versions of this, the M3713SC and the M3713DM. The M3713DM is just basically a simple diode rectifier. It basically just rectifies via a 6-pulse bridge and places DC power and provides that to every VFD. It does not have the ability to pre-charge your VFD. So basically you need to consider that when you're making any designs using the M3713DM. The M3713SC basically uses SCRs to phase in power, and that way it can pre-charge your drive. With this, you can also connect your braking solutions to the DC bus. You do not require to have any diodes or diode modules in this setup. You just connect straight to the power supply, and from the power supply you can connect directly from the DC distribution block to your regen or to your external braking transistor. So there aren't too many design considerations to worry about using common bus power supplies. Basically you just need to connect from the DC bus of the power supply, the 3-phase power supply, to your drives. The only thing you really have to be aware of is how your drive is able to pre-charge itself. If it has a resistive pre-charge circuit and it's in series with the DC bus connections, then you can use the M3713DM. Otherwise, I would really recommend just getting the M3713SC with pre-charge. If your drive already is pre-charged and you're using the M3713SC, it will not really influence how your drive pre-charges. It might just take an extra 1 to 2 seconds to pre-charge. But that's not an issue having 2 separate pre-charges. The power supply needs to be sized in order to handle basically the total rated power of the attached drives. Um, Basically, the power required from the M3713 power supply is just going to be dependent upon whatever the load is. And if you really do have a large load and you need to get more than what Bonitron can offer, we recommend placing our power supplies in parallel. The only thing that you need to remember if you're placing power supplies in parallel is that each power supply needs to have its own line reactor. And there will be a 10% D rate from total power. And a 10% D rate occurs because there might be uneven sharing between one power supply to the other. And that's just our own built-in overhead. Basically just because we don't know what design or what the system, actual real-world system might look like, and what small differences, in wire length might be. So that's why the D rate exists. So this is just from our manual, and it basically just describes how basically connect a common DC bus using our M3713 SE. The M3713DM would work the same way. It just does not have the pre-charge. Yeah, basically three-phase input comes in here. You can either use a circuit breaker or a fusing. Of course, we recommend fuses, especially quick-acting fuses. But if your system requirements are different, that's fine. The line reactor, if required, basically goes down to the M3713, which rectifies it, and from there it gets distributed to the VFDs as required. So, as a side note, basically you can also create a common bus using 12 pulse and 18 pulse rectifiers. And the way that Bonitron does this is by basically using our M3713 series in parallel with an 18 pulse phase shifting transformer. Are there 18 pulse or 12 pulse, phase shifting transformer. And from there, it creates a DC bus, which you can attach whichever regular 6 pulse VFDs and use that for your common busing for 12 and 18 pulse systems. So Bonitron also provides single phase power supplies, and you can use this to actually create a common bus as well. It works very similar to the M3713 series. Basically, you just connect it to the DC terminals of your drive and use that to provide a DC bus. It will still share current with each other, and you can still use external braking solutions if that's what your design is. With the 3712, we do strongly recommend using a line reactor no matter what. This is basically because the 3712 does produce a high inrush current because it's just the physics of using single phase with a large capacitor bank. So to limit that higher inrush current, a line reactor is strongly advised. So some design considerations with using our single phase power supply. The power supply needs to be sized basically to handle the total amount of power that may occur in the attached drives. The M3712 can also be paralleled, just like the 3713. Once again, a line reactor is required for each individual 3712, and there will be a 10% D rate from the total power, and that's just due to possible uneven current sharing. The issue with the M3712 that the M3713 does not have is that harmonics are a real issue, and it's very tough to get around this because basically it's a single phase drive, so basically the harmonics that will be seen are very severe. It will be the same as any single phase drive. Bonitron is currently working towards a low harmonic version of the M3712, and we hope to release that really later this year. But right now it's still in the process. Just be aware harmonics can be an issue with using the M3712, and you just need to be aware of that when designing it. So basically this is not a common bus, but this is basically how it would look. This is pulled once again from our manual. So basically the AC input comes in here. Basically the control power from the AC line is diverted to here prior to going through the line reactor. The 3712, the primary start problem, 99% of the time, is that the control power will be out of phase with the power going in. L1 and L2 will be different from what is marked AC1 and AC2 on the control board of the 3712. And once those are switched around, that solves 99% of every problem I see with the 3712 upon startup. And from there, you can create your DC bus and attach however many VFDs, as the 3712 can handle. So what we released last year was the M3645P. This is a variant of our line regen, basically allowing it to basically use the IGBTs to also act as a power supply. So this is basically a combination of the DC power supply along with the line regen. So basically, it does have the return on investment, basically because you can take the regen energy that might have been burned up as heat or caused overvoltages and downtime and return to AC line. There is a cost savings because you do not have to buy a separate power supply, and the line regen are all just right there in one package. You can read about it a little bit more on our website. Our website has great information about this, as well as our brochures. This slide just goes into a little bit more detail about how the M3645P functions. Basically, it takes our power supply without the precharge, the M3713DM, and basically incorporates that into the M3645 frame. So there's no size difference between our line regens and the regenerative power supply, the M3645P. The M3645P can also be used to replace certain older regenerative power supplies that other drive manufacturers make. You might encounter this in older systems, and we'd be happy if you thought of our line regen as this. Unfortunately, this is not the equivalent of an active front end. A regenerative power supply basically does not have the same functionality as an active front end. It's basically just a line regen, which absorbs energy and places it back on the AC line, as well as the power supply to actually feed power to the DC bus of the attached drives. So basically some considerations about the regenerative DC bus power supply. Once again, you need to worry about the pre-charge on your drive. If your drive does have resistive pre-charge in series with your cap bank, then it should not be a problem using this unit. If not, we do have an external pre-charge module, which we can provide. However, the M3645P is not capable of pre-charging anything but itself. It's just not rated for that. But one advantage of the regenerative power supply is that these units can be paralleled. The 100 amps and 300 amp units can be placed in parallel. There is going to be a 10% derate from just the peak power, not the continuous rated power. So that is one advantage of how these units work. So this is basically a small topological drawing taken from our M3645P manual, our regenerative power supply manual. So basically the line reactor is already included inside our 3645P. So no external line reactor needs to be purchased or anything. From here, you place the 3728 DC precharge if it's required to precharge your drives if they do not have their own independent precharge. And current can flow this way when it's required, when the drives are placing a load upon it. But if they're in overvoltage setting, current will flow back onto the line through this regenerative precharge, and basically just saving your drives from having overvoltage faults. So let's talk a little bit more about overvoltage solutions. Bonitron has for years provided a lot of overvoltage solutions. We can provide external transistors, resistors, or line regens. But there are certain things that you do need to consider when trying to design an overvoltage solution for your common bus. When designed properly, there is the chance to save quite a bit of money using a single overvoltage or single braking solution on a common bus. Each drive does not need to have its own resistor. Each drive does not need to have its own line regen. They can all just share a single one, but you do need to be aware of what you're doing when you're sizing this. If you're just to come with us with a list of drives on a common bus, our salespeople basically just in order to basically make sure our equipment will work, we'll just size to the whole combined braking, whole, sorry, basically just for the total rated power of all the drives. So if you have three 50 horsepower drives, we'll assign a braking solution that can take 150 horsepower of that. However, if you know that only one drive is going to be in a regenerative mode at any given time, then then you can design a solution with a smaller braking solution. So if you know that there's only one 50 horsepower drive out of the three that is actually going to be in a regenerative mode, then you can pick a line regen that's only rated for 50 horsepower instead of trying to design a system that's rated for 150. So that can save you quite a bit of money if you know at any one given one time what the average or the expected regenerative current will be. An exception to this rule is emergency braking. Emergency braking is where all the drives and all their loads are basically just need to come to a stop as quickly as possible. This provides a great amount of regenerative energy all at once, because all your drives will be stopping all at once. The best solution for emergency braking tends to be braking transistors and resistors. You just need to design towards the peak braking requirements at that time. Some customers have done this where they had a common busing, but only had on the largest drive a single braking resistor, and basically using the drive's internal IGBT and using just a braking resistor to be able to catch those high peak powers. However, you really need to understand your system and what the peak braking will be. This is only valid on very low duty cycle applications. If you do have like a constant regen that's occurring once every few minutes or once a minute, I would point you towards our line regens, because that will recapture the energy instead of burning that off as heat. So basically, this is a slide devoted specifically for braking transistors and issues that have come up in the past for braking transistors on a common bus. I'm going to reiterate once again, never use steering diodes with our braking transistors. Basically, this can just source current straight through one drive, and damage to our braking transistors can result. Only use braking transistors on a common bus if there's either a sharing diode where current can flow back and forth both directions, or if there's a common bus power supply. Never use it with a single direction diode. An issue that we address very much in detail in our M3345C braking transistor manual. It's in our application notes towards the end of our M3375T manual. Is basically issues that come up during our common DC busing for our transistors. Basically, our braking transistors do require a minimum capacitance to be present on the DC bus prior to being enabled. Basically, there's a small amount of snubber capacitance across our IGBT. And if there isn't sufficient capacitance on the DC bus, basically our small snubber cap will basically take all the energy of the switching, and basically damage will result to our braking transistor. The rule of thumb is that for every amp of braking transistor, you're going to require probably about 50 microfarads worth of capacitance. So if you have a 200 amp braking transistor, expect to have about 10,000 microfarads worth of capacitance on your DC bus at any given one time. To find out how much capacitance is in your drive, you're just going to have to read through your drive manual or contact your drive manufacturer. But our braking transistors are designed to meet the requirements of every drive. So if you have a drive series that is 200, it is rated for 200 amps, and you have a 200 amp braking transistor, you need to make sure all drives on that system that add up to 200 amps are present prior to basically putting the braking transistor on the DC bus. Yeah, so you just really need to be aware of this when using braking transistors on a common bus. Our rule of thumb is basically just to make sure that 60% of that drive capacitance is present at any given one time before using the braking transistor. And I would strongly urge you to read that application note in our manual. It's very detailed, it's very helpful, and basically it's pretty much where all these ideas on this slide are coming from. So that's why it's really important to understand the capacitance of your drives. And if you're switching drives on and off the DC bus at any given one time, for instance, if you're taking one off just for maintenance or just because it's not required at the time, you need to be aware that there still has to be enough capacitance for your braking transistor. If there isn't, and the braking transistor will be damaged just over time. I would recommend using caution when using the M3713DM. So rather than being able to pre-charge anything, it just basically puts a straight DC bus voltage across the braking transistor. They don't have pre-charge. So if there's a way to externally enable your braking transistor, that's really important for using our M3713DM DC bus power supply without pre-charge. In the case where you just do not have sufficient DC bus capacitance, Bonitron does offer DC bus capacitor banks, which are self-pre-charging from the DC bus. You can contact us if you just want more information about providing extra capacitance on your DC bus. So this basically concludes basically our general overview of basically issues that occur when you're trying to design a common bus. It's very basic, but you just need to have planning. But if you do it, you can really save money, you can save hardware, and you can save space inside your cabinet. At this time, if there are any questions, I would love to hear from you. You don't have to ask them right now if you don't want to on the text message, or if you just want to contact either myself. My email is twatkins@bonitron.com, or you can go to put your questions to info@bonitron.com. I'm happy to answer them at any time. So if there are questions now, feel free to just ask right now. I'll be online for about another 10 minutes. So thank you. Thank you for listening.